Okay, so this video shows work solutions for relationships in calculus assessment standard 1.2. The first question here is a trig equation. Notice that it's in degrees and the domain in this case has been restricted to between 0 and 120. So the first step here would be to divide both sides of the equation by the square root of 3 to give tan of 3x is equal to 1 over square root of 3. Now you aren't allowed a calculator for this assessment, but you should realise here that 1 over root 3 is one of your exact values, and using exact value triangles here you should be able to obtain the angle. Now down at the bottom we have 60 degrees and top 30 degrees. So we're basically asking here which of these angles has a tangent ratio of 1 over root 3. So tangent is opposite over adjacent. So in this case opposite 30 is the one, adjacent to 30 would be root 3. So we've managed to find that 3x is equal to 30 degrees. That of course isn't all, because anytime you take inverse tan or cosine or sine, you should be thinking about solutions from other quadrants. In this case we're working with the tangent ratio, which is positive. Tangent ratio positive in the first quadrant, so there's an answer between 0 and 90, which we've already obtained, and tan also positive in the third quadrant, which means there's an answer between 180 and 270, and that one's found by adding the first quadrant answer to 180. So in this case we end up with 3x is equal to 30 and 210, and the final step for this would be to divide both values by 3 to obtain 10 and 70. Now ordinarily when you have multiple waves here, in this case we've got tan of 3x, which would mean that would normally be 3 times as many solutions as we would usually have. You would be looking at adding 360 degrees to each of these values here and doing that twice, and that will allow you to get the 6 solutions. That would be if this domain was between 0 and 360. Now if you think about it, adding 360 to either of these will give you a value bigger than 360, but 360 itself divided by 3 is 120, so any additional values are going to be out with the domain for this question. So that's why in this case there are only 2 answers. Moving on to the second question here, we have a double angle in this trig equation, and the first step here would be to look to the formula sheet to find the appropriate substitution that will allow you to solve this equation. Now the substitution you want to use is 1 minus 2 sine squared theta, so that's a replacement for cos 2 theta, and the reason we chose that replacement was because it contains sine, our original equation also containing sine, so we end up with an equation which is exclusively in sine. Notice this is also measured in degrees, and the domain in this case is 0 to 180. Now a little bit of simplification first. Subtracting 1 from both sides leaves us with minus 2 sine squared theta plus sine theta is equal to 0, and although this is a quadratic trig equation, don't forget that you can always solve these by a common factor. So in this case I'm going to take out a common factor of sine theta, leaving minus 2 sine theta plus 1, and then taking each of these factors separately, so setting them equal to 0 and solving them. So sine theta equals 0, you're using your knowledge of the sine graph here to help you answer this. You're looking for the values of theta which see the sine graph at 0. So a quick sketch of the sine graph just to remind us exactly what we're looking for here. We want the values here and here, and often we would be looking for this one as well, but not in this case because we restricted our domain to 180. So the 2 values of theta from here are 0 and 180 degrees. from this factor, subtracting 1 from both sides, and then dividing both sides by -2 gives us sin theta equals 1/2. Again, we're thinking exact value triangles here. Hopefully seeing the ratio of 1/2 rings that bell for you. 1 to √3 triangle, 60 degrees down at the bottom and 30 up at the top, and we're asking ourselves here which of these angles has a sine ratio of 1/2. So which of these angles has opposite over hypotenuse of 1/2, and in this case 30 degrees has an opposite of 1 and a hypotenuse of 2. So our first quadrant angle in here, our first value for theta, is going to be 30 degrees. As I said earlier, whenever you do inverse sine, cosine or tangent, you should be thinking about the 4-quadrant diagram to get a second solution. Now, although we had a few negative signs floating around here, they did cancel out. They left us with a positive sine ratio, which means first quadrant, we've already got our answer from the first quadrant, and second quadrant. And our answer from the second quadrant is obtained by subtracting first quadrant angle from 180, which leaves us with 150 degrees. And it's quite nice at the end of these questions just to write out a little solution set where you can put them all in order. It gives you a little chance just to check that they're all within the domain that was specified in the question, which is 0 to 180, including 0 and 180, which means, yeah, we've got every solution. And the final question for this assessment standard is another trig equation where this combination of trig terms, you're told it's possible to rewrite it like this, and the first step is almost done for you. To solve this equation, 5 sin x plus 2 cos x needs to be replaced with the square root of 29 cos x takes 68.2. Now, on another occasion, you may well have to establish this yourself using the wave function, but then you can go on and solve equations of this sort. First step here then would be to divide both sides by the square root of 29. And then inverse cosine will give us answers for x minus 68.2. The inverse cosine of 5 over root 29, notice that we're working in degrees here. Inverse cosine of 5 over 29 is 21.8, and for the third time now, we're looking at a 4-quadrant diagram and seeing where the second solution to this comes from. We're working with cosine, the ratio is positive, so solutions from first and fourth quadrants. This is going to lead us to our first quadrant solution. Our fourth quadrant solution is obtained by subtracting from 360, which gives us a second value here of 338.2. And then to solve for x, we're looking at adding 68.2 onto both sides. So 68.2 plus 21.8 gives us an answer of 90 degrees, and then 68.2 plus 338.2 gives us an answer of 406.4. Now that should be ringing a few alarm bells, because 406.4 is obviously bigger than 360 degrees. So what you wouldn't want to do is just discount that and think it's over the range and there's nothing more we can do with that, because of course a full turn of 360 degrees, if you travel one further degree, you've travelled 361 degrees, but using our 4-quadrant diagram, that's exactly the same as starting at the beginning and travelling 1 degree, which means that an angle of 406.4 degrees actually has the same value, or the graph will be at the same value as if you were 360 degrees before 406. So we need to use that second solution of 406.4, and subtracting 360 from it will give us a solution just in the first quadrant here that will go along with 90. Now you can see that maybe more clearly if we have a little look at the cosine graph, because what we just saw there was that we were looking for value of cosine which was beyond 360. So let's just draw the graph a little bit longer there. Let's just say that thing's gone up to 406.4. This is 406.4 here. And what you might realise then is that if you track back 360 degrees, then cross through one there and back to here, and that's where 360 degrees earlier you also pick up that second solution, which corresponds in this case to a 46.4.